So it's my distinct pleasure and privilege to host Yuri for a talk on a topic I've discussed with him since I was even a student, models of computation. And through the years, we have interacted in various ways on both fundamentals of models of computation and then abstract state machine applications. And at this point, it's also very likely the last talk Yuri will give here as a resident, as he's moving to Michigan early next week. But I have no doubt that there will be many opportunities to interact with Yuri also in the future. I hear that there's a birthday party coming up in a couple of years, and it was always a pleasure to participate in these events. So, without more ado, please go ahead.
Thank you very much. It's a pleasure to return for a day. Let me see, how do I move that? So in 2008, Nahum Dershowitz, my very learned and scholarly friend, and myself, we wrote this paper where we proved Church's thesis and Turing thesis, but very technically there are slight differences. It's a technicality. For classical algorithms. Now, what do you mean by classical algorithms? Now, quantum people hijacked the word classical. It became to mean non-quantum. But our meaning was classical in the sense algorithms from time immemorial till certainly till 1950s, till 1960s. So this is the algorithm that Church and Turing had in mind when they put forward their theses. So another name for these classical algorithms is traditional algorithms or sequential. I will call them mostly sequential, because the first sort of non-classical, non-traditional algorithms were parallel, and so there was this. Those traditional were known as sequential. Now, you can generalize and generalize and generalize, and then it's not completely obvious why it should be even true. And so I had this argument implicit, published 2 years ago, but as you see, here is a prompt for today's talk. So let me read it. The Dershowitz-Gurevich paper says nothing about probabilistic or quantum computation. It does write down a set of axioms about computation and prove the Church-Turing thesis, assuming those axioms. However, we are left with justifying these axioms. Neither probabilistic nor quantum computation is covered by these axioms. They admit this, those criminals, for probabilistic computation and do not mention quantum computation at all. So it's quite clear to me that these axioms are actually false in the real world, whatever it means. For mathematical axioms to be false in the real world, even though the Church-Turing thesis is probably true. So there's a problem with scholarly papers. It takes time to read them. People skim. So he definitely didn't read. He actually probably didn't read even the abstract, where it says that this is about classical algorithms. Of course, this is a great hero of quantum computing, but That's how it is. So let me say, what is Church's thesis?
So the tone of the debate hasn't changed from the 1930s.
Actually, this discussion was quite civil. It is sure. There is another picture here of Stephen Kleene, by the way, which means in Dutch, small. Klein would be German. That's the meaning of his name. So he was a student of Church. He actually made the Church thesis what it is. He straightened it, called it thesis. Church himself called it conjecture, and spoke only about total algorithms. And the better place, the better version is the partial algorithms. So if somebody interested in history and all the subtleties, I've sent you to our paper with Nahum Dershowitz. Here I formulate a thesis. There are many forms you can formulate it. They're all essentially equivalent. So if you have an algorithm, so none of them spoke about algorithm. They spoke about calculability. But there is something that make it calculable. So this is algorithm. So if an algorithm computes a partial function from strings to strings, then it is Turing computable. How important is the thesis? I personally think it's not very. The importance is mostly historical. But that's how people are. Something historical has a lot of, seems to evoke a lot of interest. So these were much more naive times, and decidable seemed to be really decidable, and undecidable, truly undecidable. But by now we know it doesn't work that way. Okay, so decidable problems may be practically undecidable. So a good example is the first order theory of real field, which proved decidable by Tarski in 1948. It's a wonderful result, except you can't use it much. So there are people here who tried. It would be a huge boon to software verification if there was a good procedure. Also, undecidable problems may be in reality decidable, because you speak about the worst case. So they may be decidable if there's a good probability distribution on average. They can be typically decidable. So the classical, the first undecidable problem was a halting problem. And there is a tool called Terminator, which was developed at MSR Cambridge, UK, which worked with C programs. You bring a C program and it tells you whether it will halt or not. Okay. It worked pretty good, pretty well. So it probably can be improved, but the whole thing is decidability. It has a ridiculous assumption that we have unlimited resources. You know, where else in the world you make such assumptions? You know, why physicists are interested is beyond me. Physicists are very strange things. They tend to make huge pronouncements. With there are little reservations here and there which needs to be made, but are not. Anyway, so complexity theory replaced, to all practical purposes, this decidable, undecidable thing. Complexity theory has its own problem. It is asymptotic. But that's a different story. So there is something much more real, software specifications. So I came to computing in 1982 when I sort of moved cold turkey from mathematics to computer science. I wanted to understand what do they do there. So I volunteered to teach programming. And my chairman said no. I said, why not? He said, we have enough people to teach programming. We don't have anybody to teach theory. Those were the times. There was not enough theorists in computer science. I said, but if I always stick to theory, I will never learn much about computing. He thought a little and says, okay, once. You teach it once. So I taught essentially Pascal. And then I discovered that I have my little Macintosh, and University of Michigan had a huge mainframe. They actually competed with IBM. There was 7, 8 universities around the globe that adopted this Michigan terminal system. And so in any way, as far as I'm concerned, there was just 2 compilers, or one interpreter, one compiler, for Pascal, and they disagreed. What's Pascal? You're a mathematician, you teach something, but what it is, you don't know. There is nobody knows what Pascal is. There is no canon, there is no definition. So that arose my interest to all these things, and especially to specifications. And then I discovered that everybody among the theorists likes this declarative approach. So I knew these people, like Dana Scott and others. I knew they're not good programmers. So how can they teach? There is this population of programmers, engineers, who actually brought all those positions that feed us. And now you tell them, no, you're all doing wrong. Everything should be declarative, clean, high level. So my impression is that executable specifications are the way to go, and I was actually laughed at by theorists.
Can you define executable?
You can execute. So there are companies like Z. So you can invite you say, here's software I'm doing. The experts come and take a few months and they write a book. Okay? And they bring you a book. Now, nobody in your company can read this book. In the meantime, software, it's like organism. It doesn't stay in place. It's developed. Whether this book was ever reflecting the right thing, we don't know. It's useful. No, often it's useful to read it because you see their way to how they understood, and they're good, often very clever, good people. But you cannot test against the book. So what you want to have a specification which you can run and compare.
Mm-hmm. Yeah, I'm just asking, what is the meaning of run? Is a Prolog program executable? At what level of complexity do you call it executable?
Well, just that has state evolves, at the end you have run. Just normal run, anything which runs.
So
prescriptive.
Operational?
Operational, yes. Operational, executable for me, synonyms. Okay, so this is a famous V diagram of software engineering. So you start from certain problem, you refine it, go down in levels of abstraction, then you code, and then you test. Component test, subsystem test, and so on, go up. Okay, now, then suppose you discover, say, on this test, it's wrong. And in the meantime, a lot of people did a lot of work until you discovered this. So the obvious idea, which was around a lot, was to test in this horizontal ways, on the same level of abstraction. So in order to test, from my point of view, all these should be algorithms, should be operational, executable programs, high level, maybe not very efficient, but nevertheless. So I started to think how to approach it in general. And there is this theoretical problem. Can you have a more general kind of Turing machine. Of course, Turing machine is ridiculously low level. It works with single bits, yes, and one tape and so on. But can you have a very advanced, versatile computation model which is executable, operational? It's an algorithm, you can run it on any level of abstraction. So you can simulate on any level of abstraction, and abstract state machines were developed to meet this challenge. So my first thought was, no, it can't possibly work. So I said, but nevertheless, let's try. So first, I worked with sequential algorithms. In fact, the only algorithms I knew at the time. So, and so I had these machines. I can't explain them again, but let me go with my story, and then somebody wants, I'll be happy to explain what they are. So there are some people who like the ideas. The ASM community has been formed here in Europe and other places. And then we pushed it to parallel algorithms, to interactive algorithms, to all kind of, to a number of classes, each time when things are well understood, not just to algorithms. So this is the general thesis from this paper. It's in some Oxford U press, which is not available. So I just, when I thought about this talk, I went and made it, or thought maybe I want to give this talk. So I made it in archive version. So this is a more general thesis, that whenever you have a reasonably understood, okay, this is a thesis, reasonably understood class of species of algorithms, you can extend this sequential thesis to this class. Now, what are sequential algorithms? So it's probably what you think they are, but here is a very influential book by Hartley Rogers, who taught logic in MIT. This is Theory of Recursive Functions, the book in the area. So that's how he defined on page 2 of his book what he thinks informally algorithms are. So in particular, they are deterministic, without any resort to random methods or devices. Mm-hmm. So it's not that we acknowledge that we don't have probabilistic device in our algorithms. That's by definition. So there is often an impression that Turing captured sequential algorithms. And that's not true. So I'll show you some very classical algorithms. Here is Euclidean algorithms. That's the whole algorithm. But Euclid had two versions of it. One for natural numbers, and another one for lengths. Or today we would say negative or non-negative or positive real numbers, but they didn't have the notion of real numbers. They had the notion of length. So the version for numbers always converges. Version for length may not converge. It depends whether length A and B are commensurate. And only one of these two algorithms actually can be executed by Turing machine, because it cannot deal with arbitrary lengths. Here is a ruler and compass algorithm. Its picture comes courtesy of Wolfgang Reissig, who is professor in Berlin. So he, head of Petri, maybe you know Petri nets. He was the one who wrote a book on Petri nets. And for years he argued with me, whatever you can do with abstract state machines, you can do with Petri nets. And then at a certain point he started to write a review and converted. And he told me the story, one of the reasons for his conversion. He said when he took a course in standard course, what you say, where they explain you regular languages and context-free languages and Turing machines. So the professor started with giving a ruler and compass algorithm as an example of an algorithm. Okay, and then he went through finite machines, PDAs, and Turing machines. And he said, I waited when he will return. So the last lecture, he says, I raised my hand and asked the professor, what about that ruler and compass algorithm? And he said, professor became very angry. So, because you cannot put these things on Turing tape. Bisection algorithm, or you can think.
You can't put them on paper either.
Right.
There's noise. That's. Arguably, I would say arguably Turing had the right idea because it captures the fact that you can't do this on paper.
No, you can. Okay, let me see. For the Greeks, when you look at Greeks, they always speak about ruler and compass. Why? Didn't they realize that there are ellipses and so on? They did. But ruler and compass was their computer. Their computer.
And their computer had noise.
Yes.
Right, and so if you think of the algorithm abstractly and mathematically as dealing with real numbers, it's not true. Right? That doesn't model the computer.
Wait. We'll arrive to this. True. Any machine has noise.
If I may, another dimension is about non-determinism.
Yeah,
Do you allow? Okay, I'll let you go. Sorry.
Yeah, coming. There will be special slides. In fact, here there is a tiny non-determinism. There is a choice between this solution and that solution. But in classical theory, they just ignore that. Mm-hmm. So you can think bisection algorithm or Gauss elimination problem. Now you can approximate them with arithmetization, but you don't capture them as is, faithfully as is. So it turns out that, from my point of view, so the problem how to axiomatize these classical algorithms was there from the beginning. So in his beautiful paper, Turing does a lot of axioms. He doesn't think in terms of axioms, but he says without loss of generality. So, for example, the very first sentence in the key section is, we compute. I forgot exactly, but by pushing symbols around. So from the very beginning, he restricts himself to symbolic algorithms, ruling out, for example, ruler and compass algorithms. Okay. And as it goes, he made, there's only finite part of the brain is involved. So he made kind of strange things. They all justifiable, but obviously too many of them. I think the problem was difficult because they didn't have a proper abstraction. That actually relates to your point. They were thinking about algorithms which actually compute one way or another, something more or less real. But the simple axiomatization turns out to be on a much higher abstraction level when you deal with abstract structures, say abstract structure of the reals. Okay, that's why you can deal with ruler and compass, because so this abstract state. So so when I started to think about this problem, the first is trivial. Second came to me sort of obvious thanks to just being a logician. Any mathematical reality which is static is a kind of structure. So if you go to University of Washington, capture some mathematician, ask him what he is working on, some kind of structures. Topology, graphs, whatever, but some kind of structures. Okay. The third problem was difficult. It took me like 15 years. And so Kolmogorov thought about this. What he said, that steps should be of bounded complexity. Each step, not a number of steps, but there should be bound on the complexity of a single steps. So that was a challenge. So if you wish, at the end, I can explain the axioms. But so if you take these axioms, then every sequential algorithm is this. So Shor says that axioms probably are wrong. Now, I don't know, but for all these years, 18 years, so there's a quite now less substantial ASM community, and they tried all kinds of things. And there are various people, from mathematicians to engineers, very engineering people, computer scientists, and so nobody came across an algorithm which wouldn't, whether it's very high level or low level.
So Rogers had the axiom of not using continuous functions.
Yes.
Which is some precursor or a product. It's a weaker statement than
Yes, because they all thought. Let me give another example, much more. So there was a school of mathematics called constructivists, and constructivists said that only computable numbers exist, and they started to develop alternative mathematics. Certain theorems were false, because you say that always there exists a maximum, say a Weierstrass theorem, but this maximum may be reached in a non-computable real, and in their world, this theorem fail. Okay, that's a very interesting. Our famous Weyl, Hermann Weyl, the hero of quantum world, was a constructivist in his young years, and he had a bet with Polya. So he predicted that in 20 years, Weierstrass theorem will be false. And so this bet was done at the High University of in Zurich, ETH, and so very famous people signed it. So I can tell the story. I was in ETH visiting a colleague, and I see something in German on his table, and I see many famous signatures. I say, "What's that?" He said, "That's the bet." So he tells me the story, and I decided I wrote a little. I have a column in some journals, so I wrote an article about this. Asked somebody to make a good translation. Then, after 20 years, it was close to war. I think in 1938, or already was a war. So Hermann Weyl came to Polya and said, "Let's just forget about it," or something like that. So according to the bet, he was supposed to publish. The one who lost was supposed to publish in one of the best mathematical journals acknowledgement that he lost the bet, but this never happened. Okay, so what was the problem? So I have another article. I say why constructivism is wrong. It's not another respectable approach to mathematics, but it's just wrong. Why it's wrong? Because they were fascinated by this recursivity, by Turing computability. But the real world is different. So they proved some beautiful theorems. They were there much before complexity theory and knew a lot, but they were not interested. They were fascinated by this level, and that's the level where Rogers is. So in the beginning, they all were fascinated with this, working on this level where everything is somehow feasibly in the sense that you can execute steps in a feasible way. Does make sense?
Well, sure. But I mean, my takeaway of 3 is that it's a general statement to make about these phenomena of whether it's continuous computation.
So there is no obvious contradiction. Depends what's continuous. So what he was ruling out. Okay.
Well, you're ruling out making an infinite number of changes in one step, or a growing number,
yes,
unbounded number, growing number of changes beyond across steps.
So essentially ruling out analog algorithms. That's what his goal.
Yes, but number 3 rules out not only analog algorithms but a general statement. So, right.
I didn't understand. What do you say?
The starting point for my comment was that number 3 is a generalization of Rogers' number 4, where it rules out analog and continuous functions.
Probably. Mm-hmm.
So what is the definition of bounded complexity? I mean, I read the term complexity, and usually to me that's depends on a model of computation. So what is complexity?
Let me leave it after I come to bottom line, because otherwise I will never finish. I'm sorry. I'm happy to talk about it, but so let me see. So Nahum became one of the most active people in abstract state machine community, and he was interested in proving Church-Turing thesis. And in order to prove Church-Turing thesis, we had to go back somehow to the initial state. In our case, could be very rich. We rule no initial states out. So, for example, initial states may have a solution to the halting problem or whatever. So, and then, of course, there is no chance for you to compute only Turing computable functions. So you need to somehow cut it down. And this cutting down is relatively easy. There are some technical details, but so we formulated arithmetical axiom. Similarly, we could instead formulate string kind of axioms and proved, and prove that. Okay, now let me for a moment speak about numbers. What are numbers? Originally they were just 1, 2, 3. Then negative numbers appeared, rationals. 0 actually came about very late. That's why we have one DC and one BC, and there is no year 0, right? Okay, but by now we have algebraic numbers and reals and complex numbers and p-adic, so it's not about quantities anymore, and we keep going. Okay, that's quite an interesting surreal numbers. Okay. So the notion of number is evolving and widening. So there's not much you can say that all numbers are such and such. It's just analogy because such a familiar notion. So same happened to algorithms. So when Church and Turing wrote, the notion of algorithm was relatively robust. Everybody agreed more or less what are examples, so in in a way, when you see it, everybody knew what's an algorithm, what's not algorithm. I don't know any single example where people will argue, oh, no, this is not algorithm. So it was quite a robust notion. Not formalized, but robust. Now, where does it end? So the notion of algorithm is evolving and widening and getting ever more liberal. Surely new species will be introduced. So not much can be said about algorithms in full generality. So that was my original argument. Why this, not Turing thesis, but this overgeneralized version of it to all algorithms. Why should it be true? Because it would say something about all algorithms, which is very unlikely, seems to me. So there were some contrarians very early. I asked Andreas, whose example, Andreas Blas, many people here know, he thought it's from Kalmar, but I couldn't check. So that's one of the very early examples of, algorithm. Looks algorithmic, and obviously doesn't compute a Turing computable recursive function. But
depending on whether the universe is Turing computable, right?
Yes. Right.
You don't really know.
Yeah, it could be all finite, and therefore it's all. Wait a second. So touchy. So now to non.
That Redmond played such a big role in this debate.
It wasn't Redmond in the original example, right? Might have been Brooklyn. So non-determinism. From traditional point of view, non-deterministic algorithm is a contradiction in terms. Because what's an algorithm? Algorithm is a recipe which you execute exactly. Now, if you come to the fork in the road, take it. What? Take what? What kind of algorithm it is? It's a joke. Okay. I don't mean a physical fork on the bottom, forking road. So now, today, of course, they are ubiquitous. Also, interactive algorithms. So algorithms are supposed to be isolated. That's why you couldn't, measure rain. Right? It contradicts isolation. But by now, interactive algorithms are very, very common. Oops. Excuse me. So how is non-determinism resolved? It's by interaction. Now, imagine you have an algorithm, come to the fork in the road, take it. So some operating system will flip a coin for you or does something. So it's interaction. In this example with the operating system, but in general, there are interacting algorithms. In AI, there are these learning algorithms. They often learn from people, so they interact with people. And they're definitely learning algorithms. Now, we can argue, say, learning algorithm is not an algorithm. It may change its own program. So in quantum mechanics actually is very different. Before quantum mechanics, in computer science, non-determinism always is resolved by interaction with another agent, obvious agent, computer, person. In quantum mechanics, you interact with God, or with nature. So when you measure, a measurement is a collection of linear operators. And when you measure by fiat, one of the indices is chosen. So here we have a couple of experts on quantum mechanics, which hopefully will keep me honest. Nobody knows. It's kind of mysterious how it happens, but that's how it happens. So you interact with nature. But if you interact with nature and with people, that opens up a lot of possibilities. Okay. For example, that same example. What's wrong with it? It's interactive algorithms. Well, it interacts with nature.
It's not a matter of definition, though, because you might say that if something is non-deterministic, well, it's really a game, and it's playing against an adversary. Or, you can imagine lots of processes that are not algorithms.
A game is much more complicated because...
Well, I mean, when you have non-determinism in a system, you have to ask, as you say, the question of who is providing that.
Yes.
Right? And so is it an adversary? Is it cooperative? And so on. So all I'm saying is you could define that to be an algorithm, right? Something that interacts, right? Or you could say, no, that's something else. I mean, it's not clear. I mean, why would I...
Wait. So the point you're making actually is a point what I want to make. That's a matter of agreement. Do we consider this algorithm or not? Probably not yet. But it interacts with nature. It's the way measurement interacts with nature. Act of measurement is some kind of interaction. Now there it's a kind of mysterious and something happens as you measure. Here it's very openly. Now you have to fix details. What does it mean, array? So one can argue that's not quite an algorithm because is it training or not training? There are some... one can try to fix details. Instead, I'm going to something else. So let's consider this medical machine. Like CT scanner or MRI scanner, it sucks you in and makes all kinds of measurements, tests. Mm-hmm. So in the process, it computes a function. The input is your ID, who are you, and the time it was done. The output is whatever report machine produces. Okay? The machine is completely automated, algorithmic. So in that sense, I'm not making any claims. I'm not trying to convince you this is an algorithm. All I want to make to shake your belief that we know exactly what algorithm is. So do we want to consider this an algorithm? So let me simplify a little so that it produces just 0, 1, or -1. So it still can make all kinds of tests, but it plays chess. Okay? Suppose you always white, and the machine is black. It plays, and then it produces +1, -1, or 0, depending on whether the machine won, lost, or it was a draw. So here's one objection. Yes. So it doesn't compute because the result depends not only on your ID and time, but depends on whatever you say in the chess game, depends on your moves. Maybe, but your ID and time completely determines the game. Historically, that's the game. So it determines it. Also, we don't often require that all this additional data should be counted as input. When you consider, say, you have randomized algorithm giving two graphs, you want to determine whether they are isomorphic or not. Okay, you flip coins, but the input is just a pair of graphs. So it's not an algorithm because with algorithm, my component says, you should take the same algorithm, run again on the same data. Maybe, But this is legislation. This is stipulation. You say every algorithm has this property. We never agreed on this. Why should it be the case? So the whole idea of sucking you into the machine was so you cannot play two games. So I specifically tried to construct a scenario which you cannot repeat, definitely violating this requirement. Okay, so I'm coming now to the end. Is a chess-playing machine an algorithm or not? I think out of this context, when we discuss this, if you talk to somebody who says, here is an algorithmic machine, some people may accept it as an algorithm, some not. But my point is, whether you accept whether it's algorithm or not, you probably accept that there will, I just constructed this in the last few days because I was preparing this talk. Some more clever algorithms will appear. Yes, here's a guy you studied deep learning, right? So you have more interesting examples, which I have no idea what they are. Okay, so maybe learning from that point of view, the most interesting species. Unfortunately, I don't know much about it. So we have these two versions, which Great Shore confused. One is the original Church-Turing thesis for traditional algorithms, the one they had in mind when they spoke about all this. And that has been proven. Now, it's still, until now, I didn't see any objection. So in the very beginning, when I came with this, I wrote practically to anybody I knew, please attack. Give me your critique. And people seem to buy. Now, Shore still may be right, but now you take this generalized, over-generalized version. We still call it Church-Turing. They would not recognize it. And so you speak about a notion which is evolving, widening, ever more liberal notion. And you want to claim something about this. Now, of course, we can agree, we can stipulate. We can introduce new species of algorithms, but if they don't compute, whenever they compute a function, let me make also a remark. In the beginning, mathematicians who did computations, they spoke about functions. Today, computing functions is tiny zero of algorithms don't compute functions, they do tasks. They execute all kinds of things. Very few of them actually compute functions. But nevertheless, so unless we stipulate, I don't think on any point in history it can be established in any way. That's the end of it. Thank you. Okay.
Are there any reasonable restrictions on what the environment will say we do in the interactive algorithms?
So
you have restrictions on what the algorithm can do in terms of finite, bounded work, and your interface space with bounded finite as well. But are there?
So let me say two things. So in full generality, no. But I tell you, so Andreas Blas and I, we formalized so-called interactive algorithms. And our restriction was that agents may be spread around the world, but when you send me a message, it makes sense to me. So since my world is mathematical structure, what you send is an element of this world, or maybe few elements.
Finite observability.
Not about observability, but meaningful. In a moment, I'll say what I'm trying to rule out. And for this, we proved. Yes. What did we? what exactly did we prove? That if you look at one agent who interacts with many agents, but whenever he has a message, this message makes sense not to him. He may be an algorithm. He's an algorithm, but it makes sense in this world. It is an element of his structure. What he receives, or representation of an element of his structure. And this were axiomatized. There is another thing. I defined distributed algorithms, and at the time I thought in full generality, and it was used very successfully. So, for example, there was ITU, International Telecommunication Union. They had some algorithm which they programmed themselves. Then they revised it, and at a certain point, the whole thing, their system became so complicated, they needed help. So they wanted to take their system to specify it precisely, which will allow them to move forward. And so they allow to all theorists in the world, please do. Okay. And not only the SM group, which consisted of German professors, not only they won competition, but at a certain point they were the only ones, quite early, who were willing to participate. Because this thing was, for example, you can do a lot of things in zero time. Because it was not physical time, but a counter, as they realized. It's never written. Just in zero time, you can do all kinds of things. So what kind of zero time it is? So they did it, and so I went to Stockholm, gave a talk to a community of people whom I never knew on something I had no idea what it was. Just spoke about abstract state machines, kind of foundation for what these German professors did. Then and there was not a single example in the world where it didn't work. But in principle, it couldn't work. So it's pretty clear that there is no axiomatics for general distributed systems. And the reason is this: you can work on completely different levels. That was an unreal world. So you have a very clever algorithm, you verified it. Somebody comes from outside, Russian hacker, changes bits. On level of the algorithm, nothing happens. But on the level of single bits, he makes a hole and comes in. So what from the point of view of mathematical world of agent one, the incoming messages have no meaning. Okay. But that's what in software engineering they call the leakage problem. Information leaks down. So if you realize that there is an infinite variety of abstraction levels. So what I didn't prove, but I'm pretty sure the following is true: that if you consider one or maybe finite many, but certainly one, so everybody works on the same abstraction level, distributed. Well, that's how distributed algorithms are written today. What people call distributed algorithms. That is all reasonably understood. But the implicit assumption is that we all work on the same level. So when send me a message, it makes sense to me. Mm-hmm. Or at least it makes sense in my world. Okay, that's the answer.
Yeah, so you talked a lot about abstraction and isolation. And to me, that sort of, those ideas are more important to the idea of computing than this Church-Turing idea of computing function. So, in other words, to me, computing is taking the physical world, setting up its initial conditions and its boundary conditions such that its behavior simulates an abstract system. in order to simulate, you have to have isolation. In other words, you can't have information leakage from the outside world, so to speak, into your system. It has to be its own closed universe.
Or a little more general, in distributed case, you may have exchange, but exchange should be highly disciplined.
Right. So then, right. So to me, right. So input, output, or communication is secondary, right? But again, that input, output, or communication has to be at the level of the abstraction that you're producing. It can't have information that leaks in from outside. So that idea of isolation and abstraction I think is more fundamental to computation than the idea of computing a function, which, as you say, is a tiny aspect of computing.
There could be a language why I waited 8 years, because Shaw wrote his remark in 2010 somewhere. But I just recently discovered it by Googling or Binging, probably Binging, because I don't want Google to know much of me, and Microsoft already knows everything which there is to know.
Information leakage.
Right. So I was looking for something else, and suddenly it popped up.
Thank you.